let's derive the even-odd trig identities. So on the trig identities sheet, that would be these shown here. Okay, well, we could use the fact that we know that the cosine function is even, for example, or the sine function is an odd function. But let's go ahead and derive these identities from scratch. So if we start with the general definition of trig functions, okay, an initial side in standard position along the positive x-axis, and we will draw some arbitrarily oriented terminal side that defines a just completely random angle, theta, and then we pick any point we want along this terminal side, and then from there make a right triangle with the perpendicular attached to the horizontal. Okay, the hypotenuse of the right triangle is the radius, and then it has side lengths y and x. And so in this case, x is going to be negative. That's the coordinates of this point here. X would be negative in this case, and y would be positive in this case. The side lengths, based for the definition of the trig functions, general definition, for this triangle that you construct, you honor the signs of the side lengths. And then, so to evaluate the trig function of any angle, you do SOHCAHTOA on the reference angle, which is the angle of this right triangle that has vertex at the origin. But you do SOHCAHTOA honoring we're not finding the trig functions of this reference angle. We just use this reference angle and do SOHCAHTOA honoring the signs of the side lengths. But r is always going to be positive. The Pythagorean theorem, the hypotenuse is always positive, but x and or y could be negative, right? We've gone through this definition many, many times. Okay, so now we know that, so sine of theta, this angle theta, is equal to y over r, opposite over hypotenuse. Okay, so with that, let's think about sine of minus theta. Okay, so minus theta just means that instead of going in the positive direction, we would go in the negative direction. So it looks like we went about 60 degrees past the vertical, so go 60 degrees past the vertical, so we're about here. That's negative theta. And what you can notice here is that theta and negative theta are going to have the same reference angle. Right? This is going to be theta prime as well. Exact same reference angle, r, y, x. But the sine of negative theta, so it's going to be also y over r, but y in this, for negative theta, is going to be negative, with r always positive. Whereas here the y was positive. So it's going to be the same magnitude, but opposite in sign for sine of negative theta. And we can think about if this angle, if we drew this angle into the first quadrant, well, then negative theta would be in the fourth quadrant, and it'd be the exact same result. And if we drew this angle into the third quadrant, let's say, so we came here, maybe that was theta. Then going in the negative direction, you would do 180, and then you go about to, let's see, here was, you went 180, then about 60 after 180. Here you would go 180, and then about 60 after 180. Once again, they'd have the same reference angle. It'd be the exact same result. So this is just another way of looking at, of showing that the sine function is an odd function, which means that sine of negative theta is equal to minus sine of theta. Okay, now cosine theta is equal to x over r. Okay, so now if we think about minus theta again, the x it's x over r. Well, both the x's are exactly the same in this case, right? The x is for what we have drawn here. Here's negative theta. The x is negative in both cases, and similarly, you could draw theta in anywhere, and then think about the corresponding negative theta, and that's always going to be the case. And this happens because we're by definition of the trig functions, we're always making this right triangle with the perpendicular on the horizontal, and so that it always means that the x's are going to, for theta and negative theta, the x's are going to be the exact same, and then r is obviously it's always r and it's always positive, so that's why the cosine function is an even function, meaning that cosine of negative theta is equal to cosine theta. Okay, now to think about what is tangent of negative theta, we know that from the quotient identity says that tangent of an angle is equal to the sine of that angle over the cosine of that angle. So we can write tangent of minus theta as sine of minus theta over cosine of minus theta, which is, we can use these two properties here to get that this is equal to sine of theta or minus sine theta over cosine theta, which sine theta over cosine theta is tangent theta. So there you go. Tangent is an odd function. Okay, now for the remaining even odd identities, all we need to do is use the reciprocal identities. So cosecant of minus theta, okay, we know that cosecant of theta is equal to, with the reciprocal identity, is equal to 1 over sine theta. So cosecant of minus theta is 1 over sine of minus theta, which is sine of minus theta based on this identity is minus sine theta. So that's minus 1 over sine theta. Well, 1 over sine theta is cosecant theta. And there you go. Cosecant is an odd function. Okay, secant of minus theta, so the reciprocal identity for secant theta is 1 over cosine theta, so this is 1 over cosine minus theta. Cosine minus theta is just cosine theta. 1 over cosine theta is secant theta, so there you go. Secant is an even function. All right, now cotangent minus theta, we know that cotangent is 1 over tangent, so cotangent minus theta is 1 over tangent minus theta. Tangent is an odd function, so this is going to be minus 1 over tangent theta, which is minus cotangent theta. So cotangent is an odd function. And there you go. There's the even odd identities.